All right, so today we are going to be looking at 10.11, Taylor Polynomial Approximations of Functions. So we are finally getting into really, I think, why we're doing this entire unit is really these approximations and then the series that are built from them later. Okay? So go ahead and get those notes ready. We'll get started in just a moment. So if I could have your attention back up here, please. All right, so Taylor Polynomial Approximations of Functions. So today my goal really is to talk about what these are, where they're coming from, how we can use Taylor polynomials to approximate functions, and why we're doing that and all that good stuff. There is going to be a general form that we will be using, but we'll look at that tomorrow. Today I kind of want to just talk about, it is a shorter day, so just kind of talk about where do these come from, okay? So that's the goal for today. You do have, I think I gave you just four problems for tonight, 3 or 4 problems to kind of just test the couple of ideas that we look at today, okay? So our objective is that today we're going to be introducing the concept of using a Taylor polynomial to approximate functions. All right? The whole idea behind this is that this whole approximating functions came about way back in the day before they had calculators, is that they wanted to be able to do something like this. So if we look at the function e to the x, okay, it's what's called a transcendental function. And we wanted to know what f of 0.1 was. Well, f of 0.1 equals e to the 0.1. Is there really a way to do that by hand? Not really, okay? Now, we have calculators today. We take them for granted. We can throw that into the calculator and figure out what it is relatively easily. But before they had calculators, they're like, well, I don't know how to do that. Let's approximate it. Okay? So that's what we're going to be looking at. If we cannot use technology, is there a way to approximate that value? So I wanted you to think about the stuff we talked about this year. This is taking us back to a concept we looked back in, I think, Unit 4. Okay? But I want you guys to discuss in your groups, is there a way that we could possibly approximate e to the 0.1? Okay? So, go ahead and talk in your groups. Okay, so what are some thoughts out there? I heard some good discussions. What could we possibly use to help us approximate? So back in, I believe it was Unit 4, we talked something about local linearization or something like that. I think that's what it was called. And we used our tangent lines to approximate values of functions. We then did talk about, like, hey, would this be a overestimate or underestimate of this approximation? But we approximated values. Without knowing it, you're actually doing a first-degree Taylor polynomial. Okay? So, if we were to take that point at 0, and we said, okay, well, what is f prime? Well, first off, what is f of 0? What is f of 0, guys? E to the 0, which is 1, right? Okay. What is f prime at 0? Well, first off, what is f prime of x? Okay, so then what is f prime at 0? Also 1. So are we able to build a tangent line equation from that? That'd be y minus 1 equals 1, x minus 0, right? So that gives us the equation y equals, what, x plus 1? So, using that line, x equals, y equals x plus 1. So let's see, so that should be, I believe, if I can get that to go through there. Nice tangent line there. Okay? We can use that tangent line to approximate f of 0.1. So, using that, I can say, okay, then f of 0.1 is approximately, well, 0.1 plus 1, right? And so that would be equal to 1.1. So, that right here, this tangent line is actually what we call a first degree Taylor polynomial. Actually, a Maclaurin polynomial, to be ultra specific. Okay? All right. So, what we are going to be doing is we're going to be extending this idea of finding polynomials like our tangent lines that allow us to approximate the functions. Now, if we stay close to this center of 0, if we stay close, like 0.1 is pretty close to 0, we get a decent approximation. But what happens if I start getting further away? Is our approximation much good anymore? No. So that's why we need to expand this. Okay? So that's the whole idea why we have Taylor polynomials. Okay? So there are some basics behind Taylor polynomials. I'm going to go ahead and just give you some time to write this down, and then we'll discuss what we have. All right, so our Taylor polynomials, we do have a bunch of different terminology that we want to take into account here. We have our center. So if we look back, think back to the one that we just did, our tangent line that we just did with e to the x. That center was a center of 0. So wherever you have that common point with your polynomial, where they share that point, that's going to be your center. Okay? Now, if your center is equal to 0, that is a special type of a Taylor polynomial called a Maclaurin polynomial. So if you ever see it ask you to find a Maclaurin polynomial, you're just finding a Taylor polynomial with a center of 0. Okay? But if we're centered about that value, x equals c, that is our center. That's the place where they share a point. Okay? Or they kind of agree and they match up. We then have our degree. So the one that we did that was a first degree, because our highest power was power of 1. So the highest power n of the Taylor polynomial is that degree. So that if they ask you to find like a third degree Taylor polynomial, then they want you to have a polynomial that's a cubic, right? Function, so the function is, well, the one that we're approximating. So an example that we just did, that was e to the x. Notation, we will be using p sub n of x or t sub n of x. I have seen more of the p sub n, but you know, they might throw other things at you. But that denotes a Taylor polynomial. And then equation. So we have a specific way that we want to write it. So we write the terms of the Taylor polynomial in ascending order. So if we think about the equation that we got on the last problem, we said that was x plus 1. Well, really, I would want to write this, and this could be written as p sub 1 of x, and we would write it in ascending order, so we'd have the constant first, then plus the powers in ascending order. Okay, so that's really how we would write it. But we would have p sub n of x equals a sub 0, that's your constant, plus a sub 1 of x, plus a sub 2 of x squared, plus dot 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 dot, to a sub n of x to the nth power. And then and that's centered at 0, so that's your Maclaurin polynomial. If we are centered at x equals c, well then we just have x minus c. Okay? Now, one thing I want you to note, like, it almost seems like, hey, we're doing all these sequences, all these series, and now we're suddenly to just polynomials. Like, how does that all relate? Well, I want you to notice, what are these? aren't those like the terms of a series? And that's what it will actually, that's how everything will kind of get brought in together eventually. Okay? All right. So, ready to meet these guys? There you go.
Oh, that chair. Oh my.
Yeah, looks good, right? So on the left we have Brooke Taylor, and then on the right we have Colin McLaurin. So one thing that it does say is that Brooke Taylor was not the first one to come up with this idea. Mathematicians had been working with polynomial approximations for a while, but he was the one that got his name attached to it because he was the first one to actually write it all down and publish things. So since he was the first one that actually published this whole approximation idea, he got his name attached to the whole thing. So I guess if you find out a new thing, you want to make sure you publish it, right? All right. Huh? That I don't know. He may have, I don't know.
Because if he did, then it's not his fault.
True. Yeah, he's like, hey, I'm just going to plug in 0.
So
And everybody's like, that's so awesome. Right? All right. So if we look back at our f of x equals e to the x, x equals 0, our polynomial shares two characteristics with the function. One, it shares the point and the derivative value. And as I was mentioning, for values near 0, our polynomial is a good approximator. So we see our polynomial spits out 1 plus 1, or 1 plus 1, what am I saying? 1.1. And the function, if we use our calculator, is 1.105. So pretty close, right? Pretty good approximation. But as we are saying, and it makes sense, the further away from 0, our polynomial does not approximate well. Even just going over to x equals 4, the polynomial gives us 5, whereas the actual function is at 54.598. That is definitely no longer a good approximation. So how do we get a better approximation? Well, like we said, we need to get a higher degree Taylor polynomial. Okay? So, you don't need to worry about writing this down. I know some of you are. You can take a quick picture, but we don't have a ton of time, so I want to go ahead and move on to actually building our Taylor polynomials. Okay? Good? Okay. This I do want you to write down, and this is kind of what Spunden was writing up here. That for an nth degree Taylor polynomial centered at x equals c, you first want to set the point to each other, so p sub n of c equal to f of c to find a sub 0, to find that constant. Next, you set the first derivatives equal to each other to find a sub 1. Then you set the second derivatives equal to each other to find a sub 2, and so forth until you get down to the degree you're asked for. So the nth derivative need to be set equal to each other to find a sub n. All right. So I'll go ahead and give you some time to get that down, and then we will maybe try one out for our f of x equals e to the x. So let's go ahead and find a second degree Taylor polynomial centered at 0 for our function. So we already did a first degree, right? That was our tangent line. Let's go ahead and find that second degree Taylor polynomial. Kind of looking at this process, just thinking about what we just said on the last slide, setting these things, matching up the second derivatives, first derivatives, second derivatives, and so forth. Okay? Now, as I said earlier, there will be a generalized way. We'll talk about tomorrow the patterns that start happening as you increase your derivatives, and we'll look at a generalized form of it tomorrow. But for today, I kind of want us to just kind of get that idea of how we can match up the derivatives and find these higher degree Taylor polynomials. Okay? So we're going to go ahead and do a second degree Taylor polynomial centered at x equals 0 for f of x equal e to the x. So again, the first thing that we want to do, as we said on the last page, is we want to go ahead and set the points equal to each other. Okay? So let's go ahead and think. We want a second degree, so it'll be p sub 2 of x, and we will have a sub 0 plus a sub 1 x to the first plus a sub 2 x squared. Now it's just x because I'm situated at 0. I could put x minus 0. Don't need to. But that's what I want. So I need to be able to get everything the way that I want it. So I need to first set, so what is p sub 2 of 0 equal to f of 0? So we set the original value, plug into both, and we set them equal. Well, what happens to my polynomial if I plug in 0? So if I plug in 0 here, plug in 0 here, I'm just left with a sub 0, right? So this side is just going to be a sub 0. I plug in 0 into my original function. That's e to the 0. We already said that that's equal to 1. So then a sub 0 is equal to 1. We kind of already saw that when we did the derivative or the tangent line. We already have that there. Okay? So we know, let's start building our Taylor polynomial. So that's going to be 1. So we know what a sub 1 is. Okay. Now, what did I say to find a sub 1? What do I need to do? So p sub 2 prime, so we're taking the first derivative, at, let's go ahead and just do x here, so, and then f prime of x. Okay, so what is the derivative of our polynomial? So if I take the derivative of this polynomial, the constant goes to 0, right? A sub 1 times x would just be a sub 1, right? And then when I take the derivative of the last term, what would I have? Equals, and then what's our derivative of the original function? Just e to the x, right? All right, now we are going to plug in 0. So if I plug in 0, that'd be a sub 1 plus 2 times a sub 2 times 0 equals e to the 0. So what do we have? A sub 1 equals 1. All right, so I can continue building my Taylor polynomial. That's going to be 1x. All right, so let's do it again. Now we're going to do this second derivative. So we're going to go ahead and do p double prime, p sub 2 double prime of x equals f double prime of x. Okay, so I already have the first derivative over here on the left. So what's the derivative of my first derivative? If I take the derivative of my first derivative, what would we have? Just 2a sub 2, and then the second derivative of my first derivative of the function, still e to the x. I plug in 0, I have 2a sub 2 equals e to the 0. So 2a sub 2 equals, and so a sub 2 equals 1/2. So I go ahead and I put that into my polynomial. So I have 1/2 x squared. All right. And there is my answer. So remember, as we increase the degree of the Taylor polynomial, the more accurate our approximation will be 4 points further away from 0. Remember, when we did just the tangent line, if I kept very close to 0, my approximation was pretty good. But as I went further away, that line was no longer near my function. But as I increase the the degree of the Taylor polynomial, my polynomial will start hugging the curve of the original function a little bit more. And so it'll be more accurate further away. We would have x minus right here. Instead of just x, it would be x minus c, whatever we're centered at. So theoretically, I could have that in here. I could write this as p sub 2 of x equals 1 plus x minus 0 plus 1 half x minus 0 squared. So that centered at value would be going in there with the x's. Okay? Let's go ahead and throw this into Desmos and see how this looks against my function. All right, I think, yep, I do have Desmos here. Let's go ahead and clear that out. Let's put in our function f of x equals e to the x. All right, so there is my function. Let's put in the first degree Taylor polynomial, that tangent line that we found. That was y equals 1 plus x. Again, near our blue curve, the green line, like if I'm right around here at the center of 0, I'm going to have a pretty good approximation, right? But the further away that we get, the less accurate we're going to be. Well, let's go ahead and put in my second degree Taylor polynomial and see how that maybe improves things. So that was y equals 1 plus x plus 1 half x squared. So does that start getting a little bit better approximation the further away that we get? Yeah, right? It starts hugging it more. Now, it still kind of falls off when we get further than like here, right? If we start getting over here, it's still not a very good approximation. So I would need to go up my degree. Maybe get a third degree Taylor polynomial, fourth degree, fifth degree, and so forth to start getting an even better. The higher your degree in your Taylor polynomial, the closer these become, your approximation to the actual curve, further away from the center. Okay? All right, I believe we have, 6 minutes? When do we end? Oh, 21, 3 minutes. Okay. All right. So I don't know if we have time to fully do it. I had another one in here, looking at the natural log of x centered at 1. So let me go ahead and just show you what the curves would look like. The more you increase the degree. Okay? So this is centered at 1. We see that right here, right? That's where they're sharing that common point, 1. And the first derivative with the tangent line, around 1 is okay. We increase the degree, starts improving. We increase it some more. That's even better. We increase it some more. And isn't that even better than what we originally had? Yeah. Okay? So as n increases, the graph of p sub n becomes a better and better approximation of the graph f of x equals natural log of x near x equals 1. Okay? Eventually, yeah. You should. All right, hello everybody. Told you that I'd go ahead and do this this next problem here that we didn't get to in class. And so this one is asking for a third degree Taylor polynomial centered at x equals 1. And so this would be the setup that we'd have for a third degree Taylor polynomial. And so we want to go ahead and find a sub 1, or a sub 0, a sub 1, a sub 2, and a sub 3. We're going to go ahead and start with finding our a sub 0. So that's going to be setting our polynomial with plugging in 1 equal to the function at 1. And so if I plug in 1 to each of these, all these are going to go and equal 0, right? All the way through. And so my So all I would be left with, if this is 0, that's 0, and that's 0, I'd just be left with a sub 0. And then if I plug in this, that would be natural log of 1. So a sub 0 is equal to, well, 0. Okay. All right, so that's the first one. Let's go ahead and find our next one then. Let's see, second, I'm going to go ahead and set let's actually do this down here. Second, I'm going to go ahead and do the first derivative of my polynomial equal to the first derivative of the function. So first derivative of the polynomial, if I look at this and I do the first derivative, well, the constant goes to 0. This would just be equal to a sub 1 because the derivative of x is just 1. This would be equal to 2a sub 2, and I would have the x minus 1 to the first power. And then this would be 3a sub 3 x minus 1 to the second power. Again, would have the chain rule. Each of these would be times 1 with the chain rule, but since it's just 1, I don't need to worry about putting that in. So that's my first derivative of that one. And so let's see. Yeah, we'll go ahead and write that in. So that's going to be a sub 1 plus 2a sub 2 x minus 1 first plus 3a sub 3 x minus 1 squared. And then that's equal to the first derivative of the natural log, which is just 1 over x. Now, we're going to go ahead and do that. This is centered at 1, so we plug in 1. So that's going to be a sub 1 plus 2 times a sub 2 times 0 plus 3 times a sub 3 times 0 equals 1 over 1. 1 over 1. So then a sub 1 is going to be equal to 1. All right, so let's go ahead and do our next one. So I want to go ahead and do, that's going to be our second derivative equal of both the second derivative of the polynomial equal to the second derivative of function. So let's go back up here. So p double prime, well, that's 0 plus, and that would just be 2a sub 2. Plus, that becomes 6a sub 3 times x minus 1. All right, so that's what we have there. We're just left with 2a sub 2 plus 6a sub 3, and then x minus 1 equal to, and then I want to go ahead and take the derivative of that. So if I have that be f prime is equal to x to the negative 1. And so f double prime would be negative 1 x to the negative 2, or negative 1 over x squared. And so we go ahead and plug in 1, and so that's going to leave us with 2a sub 2 plus 6a sub 3 times 0 equals negative 1 over 1 squared. So I have 2 a sub 2 equals negative 1. So a sub 2 is equal to negative 1 half. All right. Now let's go ahead and do the next one. So the next one, fourth. And the last one that we need to do is going to be our third derivative, and third derivative here as well. And so if I do the third derivative, that's 0 plus 0 plus 0 plus, and I'm just left with 6a to the third. So that's 6a to the third. And then if I take my my derivative, f double prime of x equal to negative x to the negative 2, my third derivative would then be positive 2 x to negative third, or 2 over x cubed. So I go ahead and plug in 1, and I have 6a cubed equals 2 over 1 cubed. So 6a cubed equals 2. Divide by 6, and a cubed is equal to 1/3. All right. Now that I know all of my coefficients, I can go ahead and build my polynomial. So my third degree polynomial, p sub 3 of x, my a sub 0 was 0, so that would be 0 plus, my a sub 1 was 1, so 1 times x minus 1, plus negative 1/2 x minus 1 squared, plus 1/3 x minus 1 cubed. And again, we can simplify that to just x minus 1 minus 1/2 x minus 1 squared plus 1/3 x minus 1 cubed. And that would be the third degree Taylor polynomial for the natural log of x. And as I showed in class, we can go ahead and see all those different Taylor polynomials going up to a fourth degree Taylor polynomial for the natural log of x. And we can definitely see that as we increase our degree, the area where, or the region where our polynomial is a decent approximation increases, right? That region where we were a good approximation just slowly gets bigger and bigger and bigger as we increase our degree. All right. So that ends this video. Hopefully that is helpful. And if you have any questions, like always, let me know.